So let's first talk about the first problem. This problem gives you two strings S and T, and both are 0, 1 strings, and both of length n. And given an integer k, and each move you can swap Sn and Sj if the distance of I and j is less than k. Now you need to find the minimum number of moves to make S equals to T. So for example, if S is 1, 1, 0, 0, 0, and T is 0, 0, 0, 1, 1, and K is equals to 2, and you can get S to T by three moves, the three swap. The first swap is this, and then this. Yeah. And to solve this problem, first, let's make observation. And if we denote sum I to mean the number of the one in S1 to I minus the number of one in T1 to I, then at some conditions that sum I is equal to 0, we can split the problem into two parts. We can split this problem into two parts of first 1 to I and then I plus 1 to the length of S. So for example, if S is equals to 0, 0, 1, 1, 1, 0, 0, and T is equals to 1, 1, 0, 0, 0, 0, 1. And we can find out that at these positions, sum I is equals to 0. And we can split this problem into the first half and the second half. And why this is true? Because if at some positions, there are some swap that is from the left part to the right part and across the splitting line. And then this means that there must be another swap from right to left of this one, and they are crossed. So in this case, it is always better to make the left one to go these positions and make the right one to these positions to avoid the cross. And it turns out that they do not swap across the splitting line. And what is the benefit of this? It is that after we do this splitting of problems, then in each part, the one in S is either or to the right of the one in T in the corresponding positions, or the one in S is to the left of the one in T. So what we can do is, since that the swap operation is reversible, we can always think that the one in S is to the left of one in T. If it is not, then we just swap S and T. Okay, now after this observation, we turn this problem into an easier part, and at each sub-problems, we have all the S in one that is to the left of one in T. And then comes to a very magic part, is that we can turn 1 to n positions into k times n over k grid. For example, if n is equals to 20 and k is equals to 5, then we can turn this into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12, 15. Yeah. And let's mark each positions of one in S to be red. For example, this can be red and this can be red. And then we mark all the position in T to be yellow. For example, this is yellow and this is yellow. And after this representation, we'll find out that every time if we change our positions, for example, this 8, if we swap these positions to the right upper quarter, then the cost should be delta X. You can check it. And if we swap this 8 to the right lower quarter, then the cost should be delta X plus 1. And we will not swap the 8 to the left part, either left upper or left lower, because we already, in this observation, we already know that all the 1 in S is at the left of 1 in T. So we will only swap it to the position that has a bigger number. Else, then there must be a cross like this. There must be a cross like this. So we can also do a swap like this and to avoid these conditions. So after this observation, what is the total cost, or what is the minimum number of the move? What is the number of the move we need to do after we do a match? Then it should be the sum of all the delta X, which is always the same, no matter how you do the matching, plus the number of left lower red, the number of left lower red matches right upper yellow. And since this is always the same, this is always the same anytime, and the only things we need to do to minimize the number of the move is to minimize this part. And to do this, we can solve this in our not very hard, in an easy greedy algorithms. That is, you consider all the ones from all the red point, red grid from right to left, and then from up to down. And every time we match it with the lowest yellow that can match it. And if it is not, then we match it the most below yellow. And also there are many ways to do this, but this is not the important part. But anyway, after changing this problem into this type, we can solve it very easily in ON log type. Here the log may be from some data structures, or maybe a set in C++ or something else. But anyway, it is not that important. Yeah, and that's the first problem. Yeah, feel free to ask any questions. And if not, then I just goes to the problem 2. And problem 2, I think, is the easiest problem in this context. And this problem gives you n intervals L and Ri, and n integers Ki. And it has limitation that Ki is less than or equals to I minus Li plus 1. And Ki is greater than 1, I think. And for each I, you need to compute the number of j not equals to I, such that the interval j and interval I overlap with length at least ki. So how to solve this problem? You just need to detailedly talk about all the conditions. And there are many ways to talk about each conditions, but here I just introduce one. That is, for each interval L, R, and it has a limitation of k. Let's consider if another interval A, B can contribute to its answer. And there are 4 different conditions. And the first condition is that if A is at the left of the interval and B is at the right of the interval, then this means that LR is totally included in AB. So this times AB always contribute to the answer. And the second case is A is less than L and B is in the interval. So in this case, AB contribute to the answer when B is greater than L plus K. And third condition is that AB is at here. And now AB contribute to the answer when A is less than or equals to R minus K. And the last condition is that AB is totally inside LR. And AB contribute to the answer when B minus A is greater than K. And if we sum them up, then if we define the count to count the number of intervals that satisfy the limitation of the L positions is in the first part and R positions is in second part, then we can write down the formula of answer equals to calculate 1 dot L R to infinity, or calc 1 to 1 dot L plus K to R minus 1, and like this. Okay, and there are two problems remain. The first problem is how to implement calc, and the second problem is how to calculate part 4. So first, how to implement calc. Generally, we need to calc A to B, that is L. The L bound is in the A to B, and the R bound is in C to D. And if we want to calculate this, we can use we can first translate these into 4 parts. And now we change the problem into calculate 1 to B and 1 to D. And to do this, we can sort all the intervals by B and add them one by one at position D. When an interval is added, we update its answer by CNT1 to D, the sum of CNT1 to D. And this can be done in segment tree or BIT, anything you can use. You can use anything to do this. And the time complexity is n log. And the hard part 2 is how to calculating the part 4. And remember that part 4 is the number of the interval that is totally contained in the AB, and its length is greater than K. Okay, so let's denote the length to be B minus A, or this is the length of the second interval, and part 4 equals to the length. First, the length should be less than okay. This is a little bit dirty coding work. So the first, we count the number of interval that is that it has length less than R minus L. And then we minus it by the number of the interval with length less than K. Now we have all the intervals with length from K to R minus L. And then we minus it by the interval with left positions less than or equals to L, because we only want to count the number of the intervals that is totally inside the L and R. So we first minus the left position less than L, then we minus the positions with B greater than R. Same reason. And now let's look at which intervals are minus too much, are minus mistakenly. We find out that if the left position is less than L and the length is less than K, then we accidentally minus it one more time, so we add them back. So now the part 4 turned into a long formula like this. And each CNT problem is the same as to calculate each CNT is the same as to calculate our things like here. If we review B and length to be the two things that first have a bound and the second has another bound. They are the same. And then the total time complexity remains n log. And also, if you are familiar with the data structures, you can brute forcefully doing this calculation, brute forcefully calculate this in n log square solutions using the maybe tree with tree, maybe the two-dimension segment tree, but they are slow and also hard to implement. So I think the best solution to pass this problem is still detailedly talking about all the conditions. Okay, and then is the third problem. So in this problem, you are given two array of length n. The first array is A. The second array is B. You want to split these two arrays in arbitrary k segment. For example, if k is equal to 3, then you can split the two arrays each in k part, and each part should be non-empty, and every element belongs to exactly one sub-array. And you need to let AI the number of the average value of AI in the i's part should be less than the average of the value in the i's part in B. And you need to count the number of the split module 10 to the 9 plus 7. And the n is less than 500. So this problem, I think to pass this problem, this is medium one, not so hard and not so easy. And the most important thing is that for this problem, the n to the power of 4 solution is very easy to thinking of. That is using a DP. So let's define DPIJ as a context to split the first I element of the first array and the first J element of the second array, adhering to the given constraint. So, and also let's denote SAI to mean the prefix sum of the first array, and the SB I to be the prefix sum of the second array. Now, how to do the transitions? For DPIJ, first we should iterate for I prime is less than I, and iterate for J prime is less than J. And it can translate from DPI prime, J prime with the condition that SA I minus SA I prime over I minus I prime is less than or equals to SBI minus SBI, sorry, J minus SJ, J prime over J minus J prime. In fact, this is just a restate of the problem statement. If we write the problem statement down in a DP formulas, and this is just the result. So I would like to say that the ON to the power of 4 solutions is very easy and also very easy to implement only 3 lines of code. But the problem is how to optimize to faster solutions. And in fact, finally, since n is equals to 500, we need to implement our ON cube solutions. How to do this? We can think that after we decide an I, after we fix an I, then for each J and J prime, then still first, so the first we fix I. And then for each pair of J and J prime, which DP I prime J prime should be transformed to this? That is somehow like the case smallest I prime in value of SAI minus SAI prime over I minus I prime. So if we fix I and we determine J and J prime, so we get the value of these. And then we only need to sum up for the I prime that the SAI minus SAI prime over I minus I prime that is less than this value. So what we can do is every time we fix I, we sort all the I prime by SAI minus SAI prime over I and I prime. We sort it in this way. And we do a prefix sum. We do a prefix sum over I prime dimension. And then we iterate for all the J and then the J prime. And we want to calculate the answer. We just need to get this Sj minus Sj prime over J minus J prime. And then we do a binary search in the I prime dimensions. And we find out the prefix sum of this DP value. So by this means, we can speed up the solution to be n cube log. But and then how to speed up these solutions into the ON, into our n cube solutions? We'll find out that if we pretty sort the J, and for each J, if we sort the J prime by the value of SBJ minus SBJ prime over J minus J prime, then we only need to do 2 pointers to find the corresponding positions and no need to do the binary search. So the log in the binary search can be omitted, and then we can easily get n cube solutions. And that's how we do this. Okay, I think I have finished the short sharing about the problem. And then is the Q&A sessions, and feel free to ask any questions. If there are no problem now, and while you are thinking of problems, I can talk something about this year's USACO Gold problems. And the first things I want to say is that the problems are getting harder and harder. I would like to say that usually the second problem, this type of data structures, they are talked about in the platinum level. And also the first problem, it is really hard to think of, and it takes me a lot of time in the context to solve this problem. I think this is not that easy. So, and the second thing is, I would like to see, we can look at these three problems, and we'll find out that in the first problem, I think this is a problem that sync is problem one, sync is greater than the code. And in the problem two, sync is much more less than code. And in the problem three, we can think that the sync is a little less than the code, but they are somehow close. And I would like to say that you can find out that in these years, the USACO are more and more concentrate on the coding task. So I think if you want to make your USACO performance better, you can practice more on the code, and you can try to much more enhance your coding abilities. I know that many of you may love to do the problems on the code forces or the coders, and I think that this platform they are more emphasize the thinking part, but not the code part. But if you want to get a good grades in the USACO contest, then you have to really do a lot of practice on the code, how to implement your algorithm to be correct. It is not to say that sync is not important. Sync is also important, but if you know how to code, then you can get better grades. So just pay more attention on coding. Okay, so any questions?
Thanks, Xieting. One question from YouTube audience. Why I think the problem 2 is the hardest one. How can I improve?
Okay. So if you think problem 2 is the hardest, I think somehow maybe it's because the difference of Chinese competitors and American competitors. Maybe because I talk about some of my Chinese friends of this contest, and we think that the problem 2 is easy because maybe data structures are more are talked about more in Chinese. So anyway, so if you want to improve your solving abilities in the problem 2, then yeah, still this. So I think generally the coding abilities is the thing that you need to practice. Now here's the coding abilities is not to say I know the algorithms, but how to code this, how to implement this correct, how to implement this in a quick way. It is not, coding is not only these things, but coding is also how to find out a way to adjust these very long this very long detailed talking. You have very long detailed talking here and here. These are two very dirty work. And you will see that the only things you need to know is how to calculate this. And if you ask me, I would say like that this is a very classic, this is a rather classic technique in the segment tree. if you do not know this, then it means that you have to practice more problem on the data structures, and that's it. So make a conclusion. So if you cannot solve the problem 2 because you do not know this, then this means that you should do more and more data structures. But if you already know this, but you just do not figure out this problem or face some coding difficulties in these problems, then I would say just practice code and just write more problems, do more problems. And also, I would recommend you to do some problems from the China online judge, and you'll find many practice about the data structures. And do not only practice on the Codeforces or the AppCoder. These two platforms are stress. These two platforms are generally talk about the thinking, but the code you can try to practice some more on the Chinese online job, and that's it. Could you please write down the name of the website? Maybe just for some lj.ac and uoj.ac. Or okay. .com. You can try to find something in these 3 websites. Any other questions?
Yeah, no follow-up question on YouTube. Thanks. How about,
okay, great.
Yeah, maybe you can unmute yourself and discuss with our coach and lecturer. Let's wait.
Sorry. Okay.
Yeah, we can ask the student, to participate, to unmute themselves and have a direct discussion.
Yeah. Feel free to do so.
Xieting, follow-up question from the same audience. Only finish partial P1. Any suggestion?
Yeah. So for problem 1, yes, but the problem 1, this is so I think this is just greedy problem, and you know that for the greedy problem, generally we do not have many formula to solve these problems, and it is hardly depend on your insight, whether you can think of a better way to reformulate the problem. For example, whether you can think of how to rearrange the 1 to n into k times n over k grid. So this sometimes need experience and sometimes need just insight. So I think that for me, my suggestion to you is that while in the contest face this type of the problem and this type of the greedy problem, and you do not know how to solve this in your first glance, then just throw this problem. Throw a greedy problem if cannot solve at once. And only come back to it when you solve the other, when you have finished the other problem. Because the greedy problem, you really do not know when can you solve it if you cannot solve it at once. These problems are hardly depend on your insight.
If there are no other questions, then I think we can end this workshop here. Once again, thank you guys all for coming to this workshop. And we'll be starting Bronze and Silver solutions at 6 p.m. So we can take about a 15-minute break before we start the solutions. Yeah, thank you guys.
Yeah, thanks for listening and see you.
Yeah, and Ryan, maybe we can share the USACO report to all the audience.
Oh yeah, sure. Yeah, let me pull it up on my side. Okay, so XM has this USACO report card that you can try out for yourself. If you go to xcam.org, you can go to the USACO report and you can create your own report card for your scores this season. So yeah, let's see. Right here, USACO report. You can go ahead and fill this out and you get a report on your performance. And then also, XCamp is generously offering a $100 off coupon code for all students coming to this workshop. So at checkout, you can use the code CPI 100 to get $100 off the courses that XCamp offers. Okay, yeah, I think that's about it. Shanshan, do you have anything to add?
That's all. Thank you all for coming. If student who pass silver or into gold division and platinum division, we also have a coach for one-on-one free consultation. Welcome to consult us. Thank you all.